The fundamental objects we deal with in calculus are functions. So I'll introduce you the concept of functions. Different things may be related to each other. For example, an NBA team is related to a city. Celtics to Boston, Knicks to New York, and so on. Take another example. Each room in this building has a certain amount of students. Suppose I walked around and found all the amounts of students in all rooms. Let X be a room number and Y be amount of students. Then if you give me any room number, I can give you a value y that represents the amount of students in that room. I'll call it rule of x equals y. Suppose here our room is 124 and we have 30 students here. So rule of 124 is equal to 30. Here is the formal definition. A function is a rule that assigns each element x in A in a set A exactly one element called f of x in a set B. Suppose this is set A, this is B, x in A. The function f maps x to an element, f of x. Many times we write y equals f of x. Here, x is called an independent variable. Y is a dependent variable because it depends on x. The set A is called a domain, and B contains all possible values of f. It's called the range. It's helpful to think about a function as a machine. Give an input to the machine, and the machine provides an output. Is this definition clear? Good. We need to be aware of the condition in the definition, exactly one element. I'll explain this condition by the previous example. Rule of x is equal to y. Suppose rule of x is equal to y1 and y2 simultaneously, where y1 is not equal to y2. This will mean that the zoom x simultaneously has two different amounts of students, which is not possible. So this is not allowed. Actually, this rule satisfies the condition here and hence is a function. Let's look at some other examples. There are two relations given by two rules, R1 and R2. The question is, are they functions? What do you think? Very good. R1 is not a function because R1 maps A simultaneously to P and Q, which does not satisfy this condition. But R2 is a function because it maps each element to a single element. For example, R2 of A is equal to P, R2 of B is equal to P. Although P is not unique, that's okay for a function. I can even give you a concrete example. Let f of x equals x squared. Then suppose the domain consists of 1, negative 1, 2, negative 2. The range will be a set consisting of 1 and 4. The function f of x equals x squared maps 1 to 1, negative 1 to 1, 2 to 4, negative 2 to 4. So, as a function, it's okay, even though 1 and 4 are not unique. What if we let f of x equals x plus 1? Consider the same set. Then 1 will be mapped to 2, and negative 1 to 0, 2 to 3, negative 2 to negative 1. From here we can see each element in this domain is mapped to a unique element in range. This is called a one-to-one correspondence. However, this function here, f of x equals x squared, is not a one-to-one correspondence. We will learn the formal definition later. This is about the definition of functions. Is this clear? Good. I'll give you some remarks. We will consider functions whose domain and the range are sets of real numbers. although the domain and the range could be sets of something else, for example, complex numbers. You can learn that from a class complex variable. Secondly, the function we defined contains only one independent variable. Actually, a function can have more than one independent variables. And you can learn it from multivariable calculus. Thirdly, if not explicitly stated, the domain is a set such that the function f of x makes sense and defines a real number. Regarding the domain, I'll give you two typical examples. F of x equals square root of x minus 2 and f of x equals 1 over x. For this function, what do you think? What's the domain of the function? Yes, we know that within a square root, the value must be non-negative, so we need x minus 2 bigger than or equal to 0. Equivalently, x is bigger than or equal to 2. So the domain is this set. How about this one? Yes, for the rational function, the denominator cannot be 0. And it can be any other numbers. So the domain is a set x in R. Here R is a set of all real numbers, such that x is not equal to 0. A function we will consider is a curve in the xy plane. Suppose the domain is an interval from a to b. Function is f of x. Now you may be wondering what we will learn about functions. We will learn two main topics. One, derivatives. 2, integrals. Roughly speaking, a derivative at a point is the rate of change at the point, which is the slope of the tangent line. And the interval of the function f from a to b is the area defined by the curve. Intervals are about areas. Meanwhile, we will learn applications in economics. Is this outline clear? Good. Let's get into the details.